This is the key for homework 5. In this better choice reaction, we should observe that we have a secondary and a strong base, strong nucleophile up here. And if we remember from chapter 8, that combination favors E2. We'll get some substitution, but mostly E2. And so that's not really going to lead us to high yield of this substitution product. On the other hand, we know that the mercury acetate reaction gives us this intermediate, which can react with nucleophiles, including methanol, at the more substituted carbon, and we end up with a racemic mixture of this substituted product. Essentially, it's an addition of OCH3 and H across that double bond, and so the bottom one is the better reaction. Basically, all you had to do is answer that E2 is the major reaction on top. It wouldn't get us much of the product. This one, we observe that we have two different alkenes, and we can do a proton transfer and form the most stable cation. That's going to be this tertiary cation. And then, of course, we need to form a ring somehow, and that's probably going to be joining carbons that are 6 carbons apart, because we form a 6-membered ring. So probably the 1 and the 6 carbon will form a ring, and we can use this alkene as a nucleophile, and that's going to get us to, as we already counted, a 6-membered ring. And I can put carbon 6 right here where the cation used to be, and then carbon 1 made this bond, and there's now a cation at 2, and then 3 has a methyl group. And the final step could be proton transfer. If you want to rearrange to make a tertiary cation and then do the proton transfer, you can, but I don't think we really need to do that. Either way can get us to this the product here. So 3 steps: proton transfer, nucleophilic attack, followed by another proton transfer, can do the ring closing. And see here we have an intramolecular nucleophilic attack, and that involves forming a bond from one end of the molecule to the other. If we look at question 3, it's basically just predict the products. Oftentimes there are more than one step here. This one is simply hydroboration, and we know that the boron will be added to the the OH will be added to the less substituted carbon, and the hydrogen will be added to the more substituted carbon. And we've created 2 new stereocenters. There are no existing stereocenters, so we should presume that we'd form the other enantiomer as well. This one is a little more tricky. It looks like it's an anti-addition of OH across the alkene, but in order to do that, we need to put this methyl group in the same position as it was when we started. So I need to rotate around this bond so that the methyl is in the plane of the paper. And that gets me this setup, and then I have to figure out where does that OH go. Well, if I pull the methyl 1/3 of a rotation towards us and back into the plane, the OH goes 1/3 of a rotation back, and that ends up looking like that. And I think you'll agree with me that that is a syn addition of OH groups, and thus these are the reagents required: osmium tetroxide and its workup, sodium bisulfite. And so this is a syn addition. Those of you who answered MCPBA lost credit for this because it's not anti-addition of the OHs. Here, HCl would put a Cl right here. T-butoxide gives us the least substituted alkene. That's going to be this product. Here, we're trying to essentially form an alkene right here and cleave it. So the final step is ozone and DMS. And the first step is some sort of elimination. If we use methoxide or ethoxide, we might get competing SN2. If we use a large, bulky base like T-butoxide, we would not get competing SN2, and we get primarily the E2 elimination, removing that hydrogen, forming an alkene. And then ozonolysis gives us the carbonyl. This one, on the 5th one, should look familiar. It's simply deprotonating the alkyne and adding the ethyl group to there. The chlorine is a leaving group. Don't keep the chlorine behind in your product. It should be gone. The first step here involves partial hydrogenation of the alkene. Would look like that. Then HBr and peroxides, we know, puts the bromine on the end. There's no scrambling of this stereocenter. It should be unaffected by the reaction. So don't put a wedge there. I'm sorry, don't put a dash there. And make sure your bromine is on the end carbon, not in the middle. And finally, we have the synthesis portion. So if we work backwards from this one, we can observe 1, 2, 3 carbons, the same 3 carbons. So we don't need to lose any carbons, we don't need to add any carbons. So that tells me that the aldehyde probably comes from a alkyne, because we know that, I should make that arrow go the other direction. Good job if you caught that. And of course, this is hydroboration, followed by oxidation, and that gives us the aldehyde at this end carbon here. So the next question then is, how do I form an alkyne between carbons 2 and 3? Well, we can form alkynes through deprotonation of a dihalide. And we can make a dihalide from an alkene. We can make the alkene from elimination. So T-butoxide would be our first step. Bromine addition would be our second step. Excess NaNH2, I believe that's worked up with H2O. That gets us to the terminal alkyne. And then hydroboration of that gets us to the product. Here is an example where we have 5 carbons to start with, and now we have 8 carbons. So we need to add 3 carbons somehow. And the only way we know how to do that is via an alkyne, SN2 type reaction. If we were to turn this alkene into an alkyne, we could make this bond, and we'd somehow have to move the double bond around. And there's really no selectivity in moving the double bond from 4 to 5 to 5 to 6 to 7 to 6 to 7, because those are all secondary carbons. So there's no selectivity right there. So that's probably not the best way to do it. What if we created that bond using an alkyne on carbon 6 and 7? So we could envision hydrogenation, partial reduction of this alkyne to get to the product. And we could envision making this bond via using this alkyne anion and the appropriate starting material with a leaving group on the end. And I think we can make that starting material from what we're given using HBr and peroxides. So here's another example of sort of the reverse use of the alkyne anion. We're not going to create it during our synthesis from the starting material. We're simply going to buy it and add it to whatever we make with the starting material, and in this case that's a primary bromide. Okay, so the first one then, looks like we need to lose a carbon, because we have 7 carbons here, and I think we have 8 carbons here. So we need to lose a carbon somehow, and typically that comes from ozonolysis. And so if we can set up this intermediate, we can cleave the alkene and end up with our desired product. A lot of you may have been thinking alkyne in this case, but the alkyne, remember, doesn't require the loss of a carbon. And so you either just somehow forgot to include this methyl in the rest of your synthesis, or it just got accidentally lost somewhere. So an alkyne is not the right track to take for this first, we'll call it A, the A synthesis. How do we get to this alkene? Well, of course, that can be achieved via Hofmann elimination of this tertiary bromide. How do I get to that tertiary bromide from a secondary bromide? Well, that's simply moving the leaving group. So if I start down here Here's my bromide, and I eliminate using the standard Zaitsev conditions. I can get this alkene, and of course just general HBr, Markovnikov addition, can get me to my tertiary bromide, which is up here, and then I can use the large base to eliminate to form the alkene on the end of the chain, and then O3 followed by DMS gets me to the desired ketone product. So that's the synthetic route for A.